Hi, I'm Chris Brown, and this is lecture 2.15b in axiomatic design and manufacturing processes. And so for the next few minutes, we're going to be talking about forces in machining. Our objective is first to appreciate force calculation in manufacturing and how this is done, and then to understand how this analysis supports new product development and manufacturing process development, as well as tool development. So why machining? Well, almost all manufactured goods presently are within a couple steps, or no more than a couple steps, from a machine that cuts metal. The tooling, the molds, almost always involve metal cutting, abrasive machining, grinding, or electric discharge machining. These are all methods for material removal, and so the traditional metal cutting and abrasive actually have got the same sort of basic chip formation mechanisms that we looked at in the previous lecture, and we'll be looking at in more detail now. Because EDM is spark erosion and has a completely different mechanism for material removal. And we won't be looking much at that. But this tendency to be only a couple steps away from a machine that cuts metal is probably going to change with the rise of additive manufacturing, and more of the molds, for example, could be made by additive manufacturing. And we'll be looking in more detail at additive manufacturing in some later lectures. So where are the forces coming from in manufacturing, and in particular in machining? Well, forces in manufacturing come from deformation, and machining it's for chip formation primarily. There's also friction in machining and in other manufacturing operations. And then there is some force that's required to run the machine and overcome the friction and the inertia in the machine. The consequences are deflections, both of the part and the tool, and these lead to errors in the form and can lead to chatter and poor surface finish. The consequences, of course, of the force and displacement together are work, and this can be dissipated in heat, and it can wear out the tools. And so changing the temperature is going to make it more difficult to hold tolerances, and tool wear will also make it more difficult to hold tolerances. So here's our straight down view looking at turning, and this is the same view that we were looking at in the previous lecture. And so T1 is the uncut chip thickness, and this is the feed modified by the cosine of the side cutting edge angle here. So as the side cutting edge angle goes to 0, the feed and T1 are the same. So and as we noted previously, we can calculate the shear angle from T1 and T2 and the rake angle given by this formula, and that's just straight geometry and applies to cutting metal or cutting ice cream. As long as you're scraping the ice cream. All right, so smaller shear stresses result in, smaller shear angles result in a larger shear plane and therefore greater forces. So the force is the dynamic shear stress times the area of the shear plane, and the area of the shear plane is the thick T1, the thickness, uncut chip thickness, times the width divided by the sine of the shear angle. And I apologize there for the different symbols. For some reason, it picked up a different symbol. But, all right, it's the same as the shear angle here. So Merchant, who we spoke about previously, developed this what's called Merchant's circle diagram for decomposing the forces in machining using different themes. Now, the circle is a handy way of doing this, and these kinds of geometric properties were exploited before computers because it made a nice graphical solution. So the total resultant force here, P, is the diameter of the Merchant circle. And then this can be decomposed by chords. And if the chord starts at one end of P, and the second chord that I'm adding to it ends at the other end of P, this will be a right angle. So we end up with orthogonal orthogonal systems of forces for decomposing this, and we'll be looking at this in more detail later. What Merchant is supposing, though, in the assumptions, are that the chip forms in shear on the shear plane. So this is an approximation, obviously, because if it actually did form on an infinitesimally small plane, the shear rates would be also infinite, and that's not possible. So it is a small shear zone. And as I mentioned in the previous lecture, if you go online, you can find some videos of orthogonal chip formation. And you can see that this is a relatively thin zone. Now, if the material has more of a tendency to work harden, this will become a broader zone. And if it has less of a tendency to work harden, it'll be a smaller one. The shear rates, though, are especially high here, and are of often of the order that you find in armored penetration kinds of problems. So another thing is that the chip is held in a kind of static equilibrium by the forces on the shear plane here and on the rake face of the tool. And we notice, as we noted before, the tool really only touches the chip. And so the tool is pushing against the chip, and in this idealization, there's no forces transmitted from the tool to the workpiece directly. Why is this a kind of static equilibrium? Well, that's because the inertial forces are negligible compared with the friction and the shear forces. So we have the shear forces here in the shear plane, friction forces here in the rake face of the tool. And those are so large that they dwarf the inertial forces, because the material in the chip is accelerating as it goes across the shear plane. So there are inertial forces there, but they're just so small compared to the other ones that we can neglect them. All right, so let's take a look at this force decomposition, what we have. Okay, there's three angles to keep track of. We have the rake angle, which describes the geometry of the tool, which is highly simplified. Notice it comes to a sharp point. We have the shear angle that we've spoken about, and that's the angle between the shear plane and the direction of motion of the tool. And then we have the friction angle, which is shown here, which is, and we'll look at that in more detail, but that is the tangent of the friction angle is equal to the friction coefficient, and is the tangential friction over the tangential frictional force over the normal force. And in this diagram, we've translated some of these, or moved some of these angles so that you can see, yeah, this is alpha down here as well, and that's tangent, or tau minus alpha there. So anyway, so we have the three angles that are important. And then we have three force systems, and each one totals to P, and we'll show this in a moment. But here's cutting and thrust. So the cutting force is in the direction of motion. And so this is the force that is doing the work. So that's why that is important. This is the force that's holding the tool in the cut. The shear force, this is the force that's applying the shear stress that is necessary to form the chip. The normal force to the shear plane here, this can be used sometimes to suppress crack formation, but this is a result of the machining forces. So we've got cutting and thrust, shear and normal to the shear plane, and then we've got friction and normal to the rake face, and those are those two forces. So three force systems. Now, each of these, here's the frictional component, here is the cutting and the thrust, and here's the shear and normal to shear plane component. Each of these vectorially adds to P. And so here we've depicted a couple of them. And what we're doing essentially when we move from one of these systems to the other, because they are all, each one of these by itself is collectively exhaustive, mutually exclusive description of P. So it's a nice decomposition. But we can alternate, right? We can change these. This is one theme of decomposition. This is another theme, and this is a third theme of decomposition. So in this, here we see the relations between the frictional and normal force of the shear plane with the cutting force and the thrust force. This is often useful because also in the lab we tend to measure the cutting and the thrust force, because we can orient the dynamometer that way since we know which direction we're moving the tool. And so So that's the normal thing to measure, and then we'd like to calculate, say, the friction of the normal force. And so here's how you do it. And it's an axis rotation direction cosine kind of problem that you may recall from analytical geometry. So what we're doing essentially is a dot product, and using the angles that you could see on the previous slide, for example, and you could work them out here. From alpha, you can see, all right, all we're doing is just moving from one coordinate system essentially to another. And this composes what we'd call the direction cosine matrix in a coordinate transformation problem. So here is another depiction of the same operation that we were just looking at, going from the cutting and the thrust force to the friction and the normal force, with just a little bit more of a breakdown of the angles. So the ratio of the frictional force on the right face of the tool to the normal force on the right face of the tool is the friction coefficient. So it's tangential to normal, as in classic sort of friction analysis, and there it's shown there. Now the friction angle tau is the arctangent of the friction coefficient, or the arctangent of F over N. So the rise over the run. All right. So we can take a look at the friction and substitute in the previous equation and make a little trig simplification. And so we can show what the friction coefficient is directly in terms of the thrust and normal forces and the rake angle. And here is a similar transformation to what we were just looking at, except now we're going from cutting and thrust to the normal force in the shear plane and the shear force in the shear plane. So we can go from any one of these to any other one. All right, so here's an interesting question. And as we noted before, and we can observe again here, there's nothing in the tool that says what this shear angle needs to be. The chip is essentially free to form at any thickness that it likes. So how can we figure out what the shear angle is going to be before we start cutting? As engineers, we like to be able to predict the future. So what kind of physical principles can you draw on to predict what the shear angle is going to be? So what Merchant worked out is that this is something like a minimum work or minimum force kind of problem. In other words, the universe tends to behave in such a way as to minimize the effort that it has to apply for something. And so the chip is going to form at an angle such that FC is a minimum. So this is a classic calculus kind of problem. We'll take the derivative of the shear angle with respect to FC. Now to do that, we've got to write FC as a function of the shear angle. And so here this representation is, and this can be worked out from our previous equations. So FC, and then you have to take the derivative. And this requires, and with some simplification, you arrive at what's called the Merchant equation. This gives the shear angle is 45 degrees in radians, or pi over 4, minus the friction angle divided by 2 plus the rake angle divided by 2. So we can see as the friction goes up, the shear angle goes down, and the forces go up, as we would expect. And as the rake angle goes up, in other words, as we tilt this back some more, the shear angle is going to go up, and the forces will go down. So as we get like a skinnier knife or a flatter angle for cutting, the forces are less, and this kind of makes sense. So we found two ways now I've explained two ways of finding the shear angle. One is geometric from the chip thickness, using the chip thickness ratio and the rake angle. The other is kinetic from the machining forces, using friction and normal forces to get the friction coefficient, then getting the friction and the rake angle. So you get two ways of finding the shear angle. There are some textbooks which give you more information than you need, and it is conflicting. And I have seen problems in textbooks where the shear angle from the geometry is different than from the forces, but it's supposedly one problem. Anyway, so here's a question: how can we use this? So how do forces change with the shear angle? Now, if a very good machinist can pick up a chip, be careful because it's often hot and sharp, but can feel the thickness of it or mic it. You can mic it and get the thickness. Make sure it's detached from the workpiece and not moving around and not hot, and you don't cut yourself on it. But so you can measure the thickness, and you can figure out what the shear angle is. And so here's how does the shear force change? What is the shear force ratio for two different shear angles? So here is the shearing force, which is the dynamic shear stress, S sub D, times the area of the shear plane, A sub S. So here's the area of the shear plane, as we said before, divided by sine of the shear angle. And now here is F sub S. So the shear force is going to be the shear flow stress times W times T1 divided by the shear sine of the shear angle. So there's the force. So now if we've got two different shear angles, we take the ratio here, since the force is inversely proportional to the sine of the shear angle. If we have two different shear angles, which we can identify with two different chip thicknesses, and we calculate what those are and the sine of those are, then we know what the ratio of the forces is. Just some thoughts. We were talking about dot products, or you can use dot products to develop the direction cosine matrix. Power is going to be force, which is a vector dotted with velocity, so power is a scalar. Or it could be torque dotted with the angular velocity, and that will be power as well. Work is force dotted along with the distance, again both vectors, or torque dotted with the angular displacement. And the vector cross product, okay, it's the force like across the lever arm is going to be the torque. And so remember, the cross product is the magnitude of one times the magnitude of the other times the sine of the angle between them. All right, so here's an example of some measured forces from some work I did in Switzerland years ago, printed out on an old computer. But so we're looking at Fx, Fy, Fz, and one of the things I want to note here is the variation in the forces. We actually had the computer calculate some statistics on this, giving us the mean, the median, the range, and the standard deviation. Now, in this case, Fz is the cutting force. The reason I've done this is, as a graduate student, people would give you, I saw papers that published only one number for the forces, and when I was measuring forces and seeing all this variation, I thought, why isn't it smooth? I thought it was going to be smooth, and it isn't, right? There's some variation in it. All right, here's a result of a little experiment I did as part of my doctoral work years ago. But changing the feed, we look at the resulting cutting force, and we find there's a very linear relationship here. There's one of these that kind of failed a little bit, but the rest are quite linear. And so we're looking at different rake angles here, 6, 0, minus 5, and minus 15. But what we notice is that as we extrapolate down to zero feed, we don't hit zero force. So there's some sort of residual cutting force even at zero feed. And we can think of different reasons for that. Largely, one of the first things that should come to mind would be the rubbing of the flank face of the tool against the workpiece. So what kinds of questions should we expect to be able to answer now? All right, so given the chip thickness and the cutting conditions, what's the shear angle and the rake angle, what's the friction coefficient? Given the cutting force and the thrust force and the rake angle, what are the forces on the rake face? What is the shear force? And given the shear angle and the cutting conditions in Fc and Ft, what is the dynamic shear stress? So these are kinds of questions that you could answer. All right, so here's one thing to note as well. The tool and the workpiece can work like cantilever beams. So usually the tool has got some overhang and is sticking into the part somehow, but it's cantilevered. And here's an interesting thing. Note that for the cantilever deflection, the amount of deflection is equal to the cube of the beam length. So, so the beam length here, L, doubles. The deflection is going to go up by a cube of that, or a factor of 8. And if you have the workpiece just held in a lathe and hanging over, we have the same sort of relationship there. So there can be problems with chatter. Now, one of the interesting things to note about chatter too is that there are stability lobes. And so the tendency, if you're machining and you run into chatter, is to back off on the feed or on the speed. But if you're setting up for a large production run, you're going to slow things up that way. And so you can increase the speed or increase sometimes the tool overhang and get away from a chatter regime that way because it goes in distinct lobes. All right, reducing forces in machining. This is often desirable for obvious reasons. So one thing is, how can we reduce the material strength under the special conditions that it has in this shear zone? Another is to look at the interaction with the tool. And so this can be done with different additives, but you're sacrificing strength, so that's a coupled situation. So we could try decreasing the friction. Now the friction here that we're talking about is between the tool and the rake face, the chip rather, in the rake face. Now the conditions on the rake face for this friction are rather special. In fact, it's a kind of welding condition, so that you have a freshly formed surface that hasn't had a chance to oxidize or get dirty, and intimate contact with a tool, and it's usually at a high temperature and there's high loads. So the friction is not ordinary kind of coolant friction, but involves actually some welding. But this can be reduced nonetheless by coating on the tool, additives to the workpiece, although again this involves some coupling with the workpiece strength. The controlled contact tool that we mentioned last time can reduce the friction on the rake face, because if the chip is welding onto the rake face, if we can reduce the length of the contact, then we reduce the frictional forces. The other thing that I haven't noted here is a coolant can act as a lubricant, although it is difficult for the coolant to get into this interface between the chip and the tool. You can also change the geometry of the cut, so increasing the rake angle, as we noted, decreasing the chip cross-section by decreasing the feed or the depth of cut. Of course, this changes the material removal rate, so that's a kind of coupled situation. Or sometimes you can remove the chip breaker. Now the chip breaker's there in turning so that you don't get long ribbony chips wrapping around your workpiece. So but there is a price to pay for the chip breaker, and that's greater machining forces. All right, thank you for your attention.